Yeah, so I do want to say to begin with that Sarah Harris has been pushing on this. She can't be here today, but I want her to get all of the glory in your head for this. So, let's see. You all know the shape of the Morello machine, but I want to emphasize the metadata and address making the pointer twice as large, right? This is the big change that we're overcoming when we port to this new system. We'll talk quite a bit about that. So it is the Morello machine that we're targeting, which has the cherry features in our compiler. Okay. So here's the specs of that machine, and here is what it looks like. This thing's sitting in one of our offices. I will just tell you roughly what Rust does. So it's memory safe in its type system. My mental model going into this was that the memory safety was checked statically, but in fact, that's not exactly true. There are some runtime checks inserted by the Rust compiler, which I didn't realize beforehand. So here's an example of the kind of thing that Rust will catch for you. So we've declared an array here from 0 up to 8, and we're accessing index 9 there, so that's outside the array. And if we compile this with the Rust compiler, we're going to get an out-of-bounds error at compilation, so not like at runtime, as it would be with Cherry. So yeah, we get memory safety, mostly through static checking, but there are these runtime checks. And it's supposed to be a systems language used wherever C and C++ is used. So the problem is that those safety guarantees cannot be made for all systems code idioms. There's idioms that sit outside of what can easily be analyzed. And so Rust gives you this unsafe keyword, which is like a blow-off valve if you need to get rid of the constraints of safe code. But you lose the memory safety checks in the type system. So here's some unsafe code that accesses that 9th cell of the array, which is beyond, and that will happily compile and run, but we get a segmentation fault on a non-Cherry system. So these two sides of the coin, this Rust and Morello, or a Cherry system, they're providing guarantees that look like they overlap. So what's the value here? And for me, this is, Rust compile time guarantees are pretty valuable. I think for the Cherry community, they're extremely valuable because we've got a code base that's built to be memory safe. So it doesn't have memory safety errors in its safe code for the most part, well, at all. So we can import it without hitting Cherry protection faults. The flip side of this is that Cherry provides guarantees where Rust doesn't currently. So all of that unsafe code that we'd like to know is safe. The price that we pay is the safety is enforced at runtime rather than statically. So these two go together very well, we believe. So I wanted to show you a picture of the compiler, a sort of diagrammatic picture of its structure, to explain what we actually did, which was we worked at this interface between the front end and an LLVM backend. So we're just importing one of the Morello LLVM compilers at the back. This is a good time to talk about where we are and what we're going to do. So in this talk, I'm basically telling you stuff that I've told some of you before. We've been doing is updating the version of LLVM we're building against from an early Morello version to a new Morello version, which supports good performance measurements. And from here, we're nearly done with that. We're about a month away, I think. From here, our intention is to swap out the target from Morello to a RISC-V target. So perhaps targeting Chariot, but certainly trying to get a RISC-V target out. Is there anything else to say? Maybe not there. So this looks like plumbing, and sometimes it felt like it, but there were some more interesting observations that came from the process. So we did what you'd expect initially. We set up a new target, and we hooked it all together. What actually sort of changed? So the object layout was the biggest problem that we encountered, which is obviously the pointer size changes in what it's, how many bits it takes to store it. It's 128 bits. But the addressing size remains at 64 bits. So throughout the compiler, there's this assumption that a pointer size is the same as the addressing size. And effectively, we just need to disambiguate those two, separate them out. There was another attempt at building a Rust compiler previously where they just used, it was Nicholas Sim, just used 128 bits for both, and that looked really complicated to us. So we break this equality between representation and addressing size. I don't want to talk about that. So these are, this is the long version of the slides where I should have sent in a shorter version. So there's some interesting bits in the middle that got changed. So there's this constant evaluation phase in the compiler, and it currently assumes 64-bit pointers. We had to make it 128-bit. But then you have this problem that the metadata is not, what do you do at compilation to establish that metadata? So we just had to sort of make space for it and make sure it was initialized subsequently. It was a bunch of patching up of the sort of ideas behind the constant evaluation. I'm going to skip a couple of slides because there's an interesting bit I think you'll care about at the end. This foreign function interface thing is the thing that we've been spending time on in our current update to the new version of Morello. This turns out to be kind of an annoying and detailed part that we just have to troll through. Yeah. So we did performance measurement of the compiler, and you see, because we have Rust, we've got something interesting to say about performance. We can compare the hybrid mode, the pure capability mode against Rust's bounds checks, if that makes sense. So there's a certain runtime cost implicit in Rust where its type checks are not entirely, its memory safety checks are not entirely static. So we can turn off those runtime checks and see whether the performance of those, how that compares with the pure capability. In fact, let's see. Yeah, so we did a fairly chunky spread of benchmarks. Let's see, I have a picture. I am going to rush through these bits. The higher bars are the Morello. So this Morello compiler that we've done does not measure performance as accurately as it should, but we see a kind of 30-something% slowdown as an upper bound on what we expect to see from a cherry architecture. We're expecting this to drop with the new version of the compiler that we are about a month away from releasing. So there's an upper bound on performance, I would say. I wouldn't use this as an indicative cost. Yep, so we have a paper about that. You can check out all the details there. I wanted to kind of get to this, so I've rushed through those bits in order to talk about this. So we have this difference between pointer representation size and addressing size that costs you something. It's a change. What we wanted to do was to come up with some measurement over the Rust code base to try to figure out whether there were any choices in programming that would bump into this change and cause, what is the cost of porting, effectively, the Rust code base to our Morello compiler. So what we came upon was the possibility of running a crater run. So this runs a lint over a massive amount of Rust code, and we found some lints, actually written by Ralph Young, that were for pointer provenance, that catched idioms, programming idioms, that would need intervention if you were porting to be above our Rust compiler. And really pleasingly, the amount of code that, when we ran that crater run and checked those lints over the code base, the number of times that caused a problem was sub 1%. So the point that I wanted to make here, that I think is relevant to everyone, is the Rust code base is a source of code that, for the most part, won't fire cherry protection faults. It's already written in a memory-safe way. So this is very nice, I think, as an observation. Yeah, we had false negatives and false positives. This analysis was not perfect. And about 40% of the code was broken and wouldn't build. So you can check our script and see whether you agree with this analysis. So this thing, we have Mac and Linux binaries. We're in the middle of updating to the version of Morello where you can measure performance more accurately, and we have this aspiration to cover RISC-V and Chariot. We have got some support from Google in order to do this, so we are basically all set. We will just carry on. Thank you.